Thank you again for inviting me to talk. My name is John Clemens. I'm a doctoral candidate in computer science at UMBC, a university in the United States. And I'm here to talk about the Machine Learning Comprehension at Home project. I am the principal researcher behind it, and it is really a project that is dedicated to studying and understanding neural networks and complicated machine learning models. So neural networks, and the majority of our project is focused on neural networks. They're these really powerful constructs that allow computers to do amazing things that we couldn't even think about 10 15 years ago. We have autonomous cars. We have Google Translate, which you can point a camera at a sign in another language and it'll not only do the visual recognition to understand what's going on there, to do the translation behind the scenes. As these models become more and more useful, then these networks are becoming more involved in our everyday life. But a question comes up is, how do we verify that these neural networks are doing what they say they're going to do? How do we know that they're going to behave as intended? What we know is that the power of neural networks comes from their complexity. In a mathematical sense, they're over-parameterized for what they do. Unfortunately, their complexity makes it really hard to analyze a network on its own. At its heart, a neural network is a structure and a bunch of weights, which is just basically a pile of linear algebra. And not only can two networks that have completely different values for their weights still produce decent results for each individual, for the individual tasks that they have, they could be, it can be hard to tell because they can have completely different weights available on their system. So a human looking to inspect these networks, there's no way that someone can look at, as I say here, GPT-3, one of the biggest models around, has 175 billion parameters. If I handed someone an array of 175 billion 32-bit floating point numbers and said, what does this do? No one would be able to really do that. So the way that we evaluate networks now is that we test them against a sample of what we expect it is. If we're going to classify cat pictures, we take a test data set of cat pictures and non-cat pictures, and we feed it to the neural network. And if it gets most of them right, we say, woohoo, we're good. The problem is we've seen that this complexity can hide undesirable behavior within these networks. And I have some examples on this slide here, but we've all heard of if somebody puts a sticker on a stop sign and suddenly it tricks the computer vision algorithm on the autonomous car to make it think it's a speed limited sign and it accelerates through the intersection. So we often treat these neural networks as black box systems that we know work right most of the time, but we need to do a lot better. The information is there in those numbers. So can we find ways to evaluate how a neural network encodes the data that it learns, can characterize the limits of what's going on there, and better ways to evaluate that a particular model is fit for a given purpose? So that's what led to MLC at Home. It's an umbrella project for understanding the how and why of neural networks. Now, we envision MLC at Home encompassing a wide range of potential products here. The first one is just meta neural network analysis. Let's train a bunch of networks. If we're going to do an analysis of what each of these systems do, let's train 10,000s, hundreds of thousands of networks with the same or slightly different carefully controlled parameters and be able to do a comparison between them. But we also see things like reproducibility studies. A lot of recent research has shown that many advances in the field aren't reproducible in further literature. So we could imagine reproducibility studies here. What I don't see going on at MLC at home, and what I don't think we're certainly not tackling we made the conscious decision not to tackle in our field here, is we're not chasing state of the art. We're not looking for a single solution for a single neural network that will be better than GPT-3, or we're not looking for the latest and greatest image classifier. What we are looking is to understand why the next generation of image classifier performs better than they do. So MLC at Home is creative. It's currently running. It's one of the newest projects, probably the newest project you're going to hear about today. Started in July 2020. Currently has over 2,000 volunteers and actually over 8,000 computers now. Technically, we support running on Linux, Windows, ARM, CUDA, and I think we're probably the first project that actually supports ROCm as well on AMD GPUs on Linux. We've had a tremendous community response. We found that actually engaging with the community very early on has led to a lot of BOINC volunteers joining our little project out of nowhere. And it's been really great. We have forums, we have a Discord server, we have a Twitter account, and we've had some success, and we're actually going to release some results today. I'm hoping that this particular talk will be a bit of a coming out party for the MLC at Home project. So the first and currently active project that is on MLC at Home is what we call the Machine Learning Dataset Generator. And it gets at what I was saying before, where if we want to study how neural networks encode the data that we do, one of the things we can do is generate a lot of examples of how it does exactly that. And that's what MLDS here does. We ask our volunteers to compute thousands of neural networks on their home systems. We only have a few different kinds of training data. You can see here in our picture, we keep an active scoreboard up on our website of how things are going. And once we have this huge collection of neural networks, we can start to ask some really interesting questions like, this particular neural network, can I classify what training data was used to construct it? How many examples do I need of networks that are trained with that particular training data before I can get a good and accurate understanding or classification result out of that? Maybe even something wacky like, is there a difference between models trained on a GPU versus trained on a CPU on the actual resulting models? So we're trying to collect as much data as we can about the training process, as well as building this collection of neural networks that are trained in this particular sense. We do have a paper that I was really hoping to release today. It might have to be released tomorrow because I'm waiting for the last edits to come in. But you can search for this on the name of the paper. We'll be posting it to archive. It's MLDS, a data set for weight space analysis of neural networks, and you'll see some of the results. We'll actually go over one of the results briefly here on the next slide. But to date, the volunteers in our community have generated over 750,000 sample neural networks that is played into and enabled this analysis. That is by far the largest data set I've been able to find in this field of its kind. The largest I've seen before this is maybe in the 10,000 network range. And it's been enabled by the distributed nature of BOINC and our ability to do this. So I don't have time to go over everything that you'll see in the paper, but I did want to bring up this particular result because I'm going to be honest, I did backflips when I was able to see this graph. Each one of the dots on these graphs represents a two-dimensional representation of the weight space of a neural network that was trained by one of our volunteers. And what we were hoping to see was clustering of networks that are trained with the same data set. Do they cluster together in weight space? And that is exactly what we see in this photo. This shows that maybe weight space analysis can provide us a new and interesting method for evaluating the effectiveness of a network beyond just, well, we tried it on a couple of samples and hey, it worked. This also leads to some really other interesting questions, like if I have a network that appears close to the boundary of one of these clusters, is that somehow better than a network, or somehow better or worse than a network that appears towards the center of these clusters? What does that mean? Can we generate new networks by taking this clustering from this two-dimensional mapping that we have from our 136,000 dimensional space for weights? Can we generate new networks artificially without going through training that take this clustering into account? So feel like there's a lot more science to be done here, and we've only just scratched the surface. And all this is made possible with the data set that we've been developing, that volunteers have been computing with MLDS. So I'm going to keep this brief because I know that we're trying to catch up a little bit, but MLC at home right now, we feel like it can be around for the long term and be an umbrella project for these type of machine learning research. We think there are plenty of fun and interesting questions that we could ask and science we could do with the volunteers and the compute power that we have with us. MLDS itself is going to continue going. We're on our way to 1.1 million networks created, and we have plans for more. Currently, the networks we're creating are recurrent neural networks, but we have plans to add convolutional neural networks, straight fully connected networks, and transformer examples to the data set as well. So we consider the data set to be continuing and rolling as we go forward. We do have some needs, however. If this project is going to continue to grow and get some legs, we need more scientific collaborators, both to drive new projects to go forward, and also to look at the data set that we have released. You can go and download our data set right now off of the website. And I do encourage people who are interested in the project to please do go to our website. We've tried to keep as much information there as we can about the science that we're doing. Currently, I keep saying we, but in reality, this project is me. I could use some technical help as well. I need to concentrate on the science and finishing up my particular research. So if you're a C++ developer, all the clients we have are open source. Yeah, we could use any help that we can get along those ranges, both from data scientists to help analyze the data, and from developers to help make the client experience better for everyone who's involved. So if you're interested in helping advance our understanding of machine learning and AI, then please consider looking at MLC at home and the work that we're doing there as and contributing some of your cycles there as well. We hope to use the work from here to make AI a safer and a safer proposition to use for everyone in the future. We have both CPU and GPU work units, and CPUs are still incredibly valuable even in the machine learning context. So please don't hesitate to bring whatever compute resources that you have to bear. I did want to take a quick step back and just say that in response to some of David's comments earlier, I'm a part-time grad student. So the fact that BOINC exists and I was able to take this project and stand it up and get way more data to help support the thesis that I'm working towards, using BOINC, using the infrastructure that many of the people in this call have developed. I'd like to think that at least this particular project is proof that we've achieved at least some of the goals with BOINC. Yes, it could be easier. Yes, I could go on for a long time about the technical issues or things we could do better, but it has been a very rewarding experience and has enabled science that would not have been possible for someone like me until now. So with that, I'll open it up to any questions.